define and okay, so last time we stopped at this point. We said that at the end of this chapter 1, we are going to look at these some introductory concepts for operating systems. Actually, these are actually our chapter numbers. Okay, this is chapter number 2. This is chapter number 3, chapter number 4, and chapter number 5. Okay, and we will make an introduction to these concepts first, and later we are going to look at these ideas one by one. But the main ideas will stay the same. The chapters will be details, the details of them. So let's look at these processes, and we did that before. We gave a definition for the process. We said that basically it's a program in execution. Without a program, there is no process, but program is not the only thing that the process has. Process is a program in execution. What does that mean? That means that a program, while it is being executed, it has a definition for address space. Okay, it has a process table. Inside the process table, you have many items of data, such as the registers, the open files, the memory usage maps, and etc. They are all stored in this page table. So whatever that page table has, it belongs to the process. And as you see, these registers. Remember the register, some people take it in a wrong way. So this is our CPU. Inside our CPU I have my registers. As we said, for a 64-bit computer, there are 64 registers available for our CPU. Okay, I know that. Why the registers are special? They are special because they are inside the CPU. But now we are saying that I keep those registers in a page table somewhere in my memory. What does that mean? I mean, how are you going to keep those registers inside your memory if these registers are fast or your memory is slow? Of course, I don't keep the exact copies. I keep them only when I am blocked. Okay, remember, I have a single CPU. That's my assumption is. When my process is blocked, when my process doesn't continue, okay, when it doesn't continue, what do? I keep all of my data inside the CPU in this process table, and I keep it there. It is safe. When I start execution again, I load them from this table. Okay, so that's what we do. That's why we say that we keep registers in our page table. I don't always keep my registers while my program is being executed, but if I don't have the CPU, of course I keep my registers inside this page table. Okay. So any questions up to now, up to the processes? Okay. So you are done your email? No, not yet. Are you done with your email? No. You don't use emails? You are done with your Instagram? If you're going to play with it, just go sit backward, okay?
I just sent SMS.
That's important. Yeah, that's good. Okay. So let's move on. I couldn't bring your attendance sheet now because we didn't have the internet connection for some reason. I cannot reach my printer. I will try to fix it between the lectures. So the processes. Sometimes, for a given program, you have more than one process. Okay, you say that I need, as a process A, I need 2 helpers. Okay, process B and C. Okay, and process C says that I need 3 helpers, D, E, and F. So this makes it like a process hierarchy, process family tree. Okay, so these are all working in synchronization. These are working in cooperation to complete a task. Okay, so the processes can create other processes, and they can communicate with each other, and they can that way complete the task in a more efficient way, more interactive way, more in a way that is more pleasing to the end user. Okay, so this is something common, and sometimes we refer to this hierarchy as this is a parent process, these are the child processes. Okay, sometimes we refer to it that way, and some operating systems they directly support this structure from their kernels. For example, Unix has this structure. Unix says that when the operating system starts, there is only one process, and it is called initial process or the initiation process. Okay, init process, and that process, okay, makes all the other processes. So this is the topmost parent process of all the processes. Okay, so init says that all I am going to do is I am going to start this process, and this process, etc. It goes that way. When I start my session as a regular user, when I start my session on Linux, I usually have one process. Okay, this will start. Okay, so this is my only process, my shell. Okay, and other than that shell, I have this process PS. Okay, PS lists all the processes that I am running on this computer, Nothing more than that, because there might be many other processes running, but I am not showing them. Okay, Bash is running this. Bash is the parent process of this PS. When I say give me all that information, okay, so it gives me this. It says that init is the parent process of all, Bash is the child process, another one is the PS minus whatever it is. Okay, so it is giving me all this information on Unix. Windows has a similar structure too, so we are going to look at it later when we look at the Windows operating system. Okay, so that's just a little bit detail about the processes. Okay, so let's skip to the files. Well, of course, I mean, there are many details about processes. We will talk about them later. Files for most operating systems, they have the concept of a directory. Okay, what's a file? A file is a related set of data kept in the same place on our disks. Okay, but if those data are related, then we keep them in a directory. Okay, so it's a way of grouping files together. With the files, you have this concept of directories, working directory, file descriptor, and etc. And we are going to look at them later one by one. So again, in our case, okay, when I say to my shell program, where is my working directory right now? This is my working directory. So what are the files in this directory? This ls is the command. You all know all of those. If I like to okay, if I do this, I would know which one is a file, which one is another directory. For example, this one is another directory, Java test. Let me switch to that one. Okay, and go there and ask the same question, what is my working directory? Okay, this is my working directory. Now it has changed. So these are the concepts that are almost common with all the operating system shells. And again, we are going to look at them one by one. The important thing here is that the files that are related to each other, usually they are grouped into directories, and directories are related to each other. At the top, I have this directory, root directory. Okay, in Linux systems, everybody is connected to this root. Okay, in Windows operating systems, there is no such thing as root. Okay, there are root directories for each drive, but those drives, they are not connected to a root. But in Unix systems, they have to be connected to a root all the time. Okay, so there might be some differences between operating systems regarding how the directories are kept, but usually they have this directory mechanism available for them. Okay, files are not just simple storage places for data. Sometimes there are special files. For example, a pipe. The operating system considers it as a file. It is not a classical file. Actually, it's a pseudo file. We usually use these kind of structures to connect two processes together. For example, whatever this process A produces, okay, instead of putting all the produced thing to the standard output, let's redirect it to the input of this process B. Okay, so it is called a pipe. For example, I can do this. I can do what? Let me go to my working directory. Okay, this is my ls. I can redirect it to, for example, t.txt. Okay, so instead of producing all this ls results to the standard output, which is the terminal in my case, now I have directed to a file t.txt. Okay, I have such a file now, t.txt here. Okay, t.txt is here. Okay, so I can redirect it, or I can redirect this results of this thing, this program, through a pipe to another program, which is, for example, let's count the number of lines. Okay, wc word count, and it's going to tell me that, okay, it has, I guess, 11 lines, and inside these 11 lines there are 103 characters. I guess that was the meaning of it. So WC expects something from the standard input, but instead of getting the standard the input from the standard input, I am telling that WC that there is a special file. It's a pipe file, and you are going to get your data from this pipe, and this ls is going to write everything to that file, that pipe file. And I can do this any way I like, and I can maybe say WC again. Okay, so this time I say that you have 3 words, 1 line, and 24 characters. Right? So you understand, I have 3 words, 1, 2, 3, just 1 line, and total is 24 characters. Previously it was, so this ls has obviously 1, 2, 3, 4, 5. Okay, it has 11 lines. I don't see the lines. Maybe it is here. Like this one is better. ls minus l. So this one has 11 lines. Let me do this then. Minus l and 12 lines and this many characters. Whatever. Okay, this is a special notation for this shell, and this notation is used for creating a new file, special file. It's called pipe, and these are files too. These kind of abstractions make the life of the programmer a lot easier, because for the programmer doesn't care if they are receiving their input from the standard, from the keyboard, from some other program, from a file. Doesn't matter. They just open the standard input, and they just use up all the data available there. So it becomes the responsibility of the operating system to make these abstraction for the user. Okay, so this one and that one connected by a pipe, and we are going to look at them when we look at the chapter number 4. Okay, so there is a concept, there is a in biology they try to borrow a concept, a term, a phrase that they often use. In biology, they say that, I mean, I don't know about this, it just writes in the book. Ontogeny recapitulates phylogeny. Ontogeny is embryo, okay? Phylogeny is the species. And we say that development of an embryo repeats whatever have happened to the parents of that embryo, okay? So usually we say that for the computer world, whatever happened in terms of operating system development and hardware development to the mainframes, we are going to go through the same set of steps, okay? So every new type of computer, they will go through the same development as the ancestors. What do we mean by that? Okay, in 1960s, the mainframes had very little amount of memories, 128 kilobytes of memory for a $10 million computer in 1960s. Okay, so if you don't have memory, then memory is so scarce and so valuable. So what do? You use assembly language to write your programs so that you take care of your memory, okay? You use your memory very careful way, okay? Then the technology advanced, and with the invention of the integrated circuits, mainframes had megabytes of memory. But then in 1980s, PCs had very little amount of memory, 64 kilobytes of memory. Again, we used assembly language to program those PCs those days, okay? Then in 2000s, our embedded systems, they didn't have much memory, so we used assembly language to write programs for them. Nowadays, smart cards, they don't have that much memory or CPU power. We do the same thing for the smart cards. What does that mean? Okay, it means that whatever the new type of computers are, they are usually smaller, cheaper, but they are usually weak too in terms of memory and CPU power. So we have to be very careful about these kind of resources. You are going to start again programming in assembly. You are going to start using techniques that will use not much CPU power and etc. And so we are going to go through the same phases as the previous computers. We go through the same development as the ancestors. That's why we keep talking about what happened in 1960s and 70s and 80s. Okay, because we cannot avoid it. It is not like we solved those problems and we are not going to go back to those problems again. No, we are going to solve those problems over and over again for the new types of computers, because that's what has happened. Okay, that's what has happened for the last 4 or 5 generations of computer hardware and operating systems. Okay, another similar history path. Protection hardware. What's the protection hardware again? What's the protection hardware on a CPU? Anybody? How about our online people? Do you guys hear me right? Can you hear me okay?
Yes, we hear.
Well, you hear me, but you don't see the screen, right? Because it is blurred. And nobody told me anything about it. So this is what they are seeing actually.
No, we can actually see the screen share.
We see a better quality.
A little. We see the screen a little blurry. That's because I made it blurry. Let me make it. Okay. Is this better?
Yes,
Is this
no,
better?
it's clear.
Is it clear now? Okay. So you couldn't see anything actually previously. Okay. But that's fine, I guess.
You were screen sharing, sir. We could see that your screen.
So you see my screen, but you didn't see my video. Okay.
Yes.
Good. Okay. Good. That's good. So anybody, what's the protection hardware for a CPU?
Timer maybe.
Okay. Anybody? Somebody's talking on from the online audience?
I said maybe timer can be a protection hardware.
What can be a protection hardware again, Mustafa?
Timer.
What does it say? Timers? Well, maybe it could be, but not. I mean, it doesn't have to be. What else?
There is no protection.
Who's talking? What?
Maybe there is no protection.
Well, sometimes there is no protection, but if there is, what is the protection hardware? Yes?
Maybe BIOS.
Maybe what?
BIOS.
BIOS?
Yes.
No, well, no, BIOS is a very simple operating system. It is not a protection hardware. Protection hardware is the part of the CPU that says that as a process you cannot access the other parts of the memory. You are not allowed to. That's one thing. The other thing is, as a process, you don't have privilege to execute this instruction. Remember our page tables, or remember our cache tables or page tables, or the memory map tables. Only the operating system can have access to those kind of special tables on the CPU. And protection hardware says that as a regular program, as a user mode program, you don't have the privilege to access these tables or this data. Okay? Or there are special instructions, for example, input-output instructions. I am saying that on this controller, on this video controller, I am going to write this to this video controller address, and the protection hardware says that no, you can't do that. You are not the operating system. Okay, so obviously for this to happen, the CPU has to support it. But in 1960s, we don't have the protection hardware for the CPUs because CPUs were not that powerful. Later, when they added this protection hardware to the CPUs for the mainframe computers, we had the same problem for the PCs. Okay, in 1980s and 1990s, beginning of 1990s maybe, there were no protection hardware for the PC CPUs, so there was no kernel mode actually. If I have a process, I can do anything that I want with the computer. That's why it was very common to have crashes every day of your computer, because any process can do anything that they want on that computer, and in that case everybody can crash the computer if they wanted to, or if by accident. Okay, so that's the protection stuff. Nowadays the embedded systems, they have the protection hardware too, because they are powerful enough. But smaller computers, such as the sensor node computers or the credit card computers or some very, very cheap computers, they don't have the protection mode. Okay? So that's what happens. That's what happens. That's what we are saying. Ontogeny, recapitulase, phylogeny. That's what we mean by. Of course, we don't try to say anything about the biology here. That's what we are saying. Okay, in biology they had these terms, and we are saying that the same thing is available. Okay, so that's the reason we keep talking about old operating systems such as Multics. Okay, because they had to solve lots of stuff, lots of problems, and most of those problems we are solving them again and again for the new types of operating systems, for the new types of computers. Okay, so the same thing happened in many times regarding the large memory, CPU power, virtual memory, and etc. Good. Okay, so we talked about the system calls. Let's remember that. Okay, remember this one. Read a simple library call C library call, read this many bytes from this buffer. Okay. So what do you do with this one if when this happens? Of course, I put everything on the stack 1, 2, 3, and I call the system library function read. Okay. So the system library function read cannot read it by itself. It will ask the operating system to read it. For this one, it's going to cause an interrupt. And that interrupt, of course, interrupt means that every time the operating system is in power, is in control, an interrupt happened. This time, we are going to cause this interrupt by saying that, okay, for the read, there is a special code, and I put that code inside the register, and I said, make a system call, a software trap, okay, a software interrupt, trap to the kernel, and I am in the kernel mode now. The CPU is in the kernel mode, but now operating system took over, and operating system finds the handler of that read system call, handles it, and puts the data in the buffer, whatever the buffer is, and then the scheduler takes over, okay, and the scheduler lets one of the processes which are ready to run. It will let one of the processes ready to run use the CPU. That's what happens with the system call. So a software interrupt happens, operating system takes over the CPU, it handles it, and it does whatever it needs to do, other stuff. It takes care of some bookkeeping stuff, and then gives the CPU back to the processes. That's what the system call does. Yes.
What does the step number 7 does actually? I didn't catch it.
Step number 7. It is the dispatch.
After
Okay.
dispatch, there is some
So
list.
what?
After there is some list kind of here table, right? What is it?
So the operating system says that, okay, I can do 100 different things. I can read data from some place. I can write some data from some place. I can do input output. I can give you some memory. I can do this protection based stuff. So each of the system calls has a special number, okay? So when I say, okay, I am going to call this operating system, make a system call, and my call number is number 7, or number, let's say, 31. So it looks up this number 31 here. So it says that, okay, this is the one that I like to run now. So it's a function pointer, obviously, and it tells this function to run. Now the system, that function runs, and that's what happens. The same thing with the interrupt handling. You know the interrupt handling, the hardware interrupts. When the hardware interrupt happens, how many kinds of hardware interrupts are there? Well, there are keyboard interrupts, mouse interrupts, network card interrupts, timer interrupts, etc. Right? Each one has a number. When the hardware interrupt happens, okay, this number this time is given by the interrupt controller. Interrupt controller says that, okay, there is an interrupt. Okay, what is the interrupt? The number is 7. So 7 corresponds to maybe the keyboard interrupt. So the CPU handles that keyboard interrupt. Of course, there must be a function to handle it. Who writes that function? Operating system designer writes it. Okay, and that function is part of the core operating system. Okay, after every interrupt, whether it's a software interrupt or hardware interrupt, operating system has the control of the CPU. And interrupts happen a lot. Interrupt happens a lot. If nothing happens, there are at least a timer interrupt. It happens maybe 40, 50 times a second. So CPU is on by the operating system 40 times a second. Sometimes it doesn't do anything. It says that, okay, I don't do anything now. I'm going to go back to the interrupted process, or sometimes it says that there are many things to do now. I'm going to do that. Okay? So everything is kind of turns around the interrupts. Before the interrupts were invented, okay, things were much more difficult. It was polling. So the CPU has to, from time to time, has to say, are there any input-output procedures ready to be executed, or if somebody wants me to do that kind of stuff, okay? So in a way that when you want to output something, you have to output everything yourself. So without the interrupts, operating the task of the operating systems are much more difficult.
Okay.
Yes.
Is there any time interrupts for OS itself?
What?
Is there any time constraint for operating system itself
What do you mean time constraint?
running in the CPU? Well, some processes, all processes have limited time in the CPU for running.
Yeah. Uh-huh.
Does operating system has any constraint for this?
The question is, maybe the guys at the back, you didn't hear it. The question is, are there any restrictions for the operating system regarding the time? Can the operating system use the CPU the way it wants indefinitely and doesn't give it back to the processes? Of course, if they want it, it can, but that would be a system crash, right? I mean, operating system is doing something and my word is not responding. Operating system is doing something and my email program doesn't respond at all. That wouldn't look good, okay? And they designed operating systems in a way that whatever it is doing, it is done in a quick way, okay? But there is no guarantee that, okay, Windows doesn't guarantee any operating system that are not the real-time operating systems. They don't guarantee any return time. They won't tell you that, okay, you ask me to read some file from the disk, and I'm going to read it in 2 milliseconds. There is no guarantee such thing. There is no such guarantee. An operating system say that I can take as much time as I like. I will try to be quick, but there are no guarantees. If you are giving as an operating system, if you are giving guarantees to your customers, to your programmers, okay, then you are a real-time operating system. And real-time operating systems are very rare. And if you have a not soft real-time system, but a hard real-time system, usually hard real-time systems, they don't have disks, okay, because disks are mechanical. With the mechanical stuff, I can't trust them, right? And usually they are very inefficient in terms of CPU usage because they try to be very cautious about the CPU time. Usually they load only maybe 30% of the CPU. Rest of the CPU time goes idle because you want to guarantee that if you want to do something, it's going to be done in 10 milliseconds. So you like to keep lots of CPU cycles available all the time. Okay. So basically the answer to your question is no. Operating system doesn't have to return in that time, but they try to, and they are written very, very carefully. So usually most of the time they are on time. Good. Any other questions? Okay. So let's look at these system calls. What kind of system calls we have? What did I say? Somebody asked me about what are those. What is this list? Okay. This list is this list of the system calls. And what kind of system calls we have? Let's look at them, okay? Most of the time we are going to look at these, the Posix based operating systems, okay? Portable operating system interface, Posix. Okay, this is a standard system interface definition. And all the available nowadays, all the available Unix systems and the Linux systems, they follow this standard. This standard defines about 100 procedure calls. Well, procedure calls are, they don't correspond exactly to the system calls. Most of the procedure calls are handled by system calls, but they don't have to be. Okay, they don't have to be handled that way. And Posix says that as a Posix compatible operating system, you need to handle these 100 procedure calls. And some of them are related to processes, some of them are related to files, some of them are related to timers and etc. So let's look at them one by one. Windows is not a Posix compatible operating system. Okay. Well, it has calls that are kind of compatible with some of these procedures, but not 100%. the Macintosh operating, the Apple operating system, it is based on some kind of Unix, but they don't say that, okay, we are doing this because it is Posix portability, compatibility, and etc. If you look at the book, there are two chapters. There are chapters on Linux operating system. There is a chapter about Windows, and there is a chapter about Android, but there is no chapter about the Apple operating system, because Apple doesn't document these kind of details very often. That's why in operating system books they don't have chapters about that operating system. But as I said before, I think it's starting in 2000 or 2005, they decided that their whole operating system will be based on Unix. So they are basically running Unix. So let's look at this Posix interface, Posix operating system procedure calls. And these are the ones that are about process management. In Unix, okay, in Posix systems, to make a new process, you make this process creation called fork. Okay, fork makes a new process. How does it do that? It copies the process of the calling process. Okay, if this is my memory, if this is my process running P1, this is my text, this is my code, this is my stack. Okay, it is growing downwards. This is my heap, and this is the available area. Okay, let's say I'm running this P1, and P1 made a system called fork. Fork immediately, okay, fork immediately does this. It takes this part. Can I do that way? Okay, just a minute. Maybe I should do, yeah. Okay. It says that I am going to make exactly the same process, exactly the same. Let me erase this one. Okay, so it will be now P2. So I had this one P1 here, P2 will be here, and P1 and P2 are exactly the same. Okay, byte by byte they are exactly the same, but they are two different processes, and they are running the same program with the same data. Okay, well, it looks like it doesn't make much sense for now, but that's how the Unix is designed. That's how it works. Okay, fork does that. Okay, so P1 and P2 are copies of each other. Of course, P1 is the parent of it, so operating system knows that P1 is the parent, P2 is the child. Okay, P1 is the parent and P2 is the child. But then how would I know, as a programmer, how would I know that am I running the P1 or the parent or the child? How would I know that? Okay, so the fork says that. Okay, let me give you one example. Here I called fork. As soon as I execute this line, this whole process is copied. Now I am running two of them. For the parent, this fork returns the created processes process number. Okay. For the child, it produces 0. Okay, so that's why we say that the parent part of this code will execute this part, and the child part will execute that part. Okay, remember, I mean, parent and child are two different processes. They are two different processes. Okay, since fork returned a non-zero number, which is the process number of the child, I am executing this part for the parent, and I'm executing this part for the child. That would be the difference. From after that point, They are exactly the same program, but they are executing different code. So that's how the thing. That's how the Unix system is defined. For Windows, it is different. For Unix, it is that way. And as you see, they are executing different code. Parent says that I am going to wait here. I am going to block myself until the child ends. Okay, wait for the child to exit. This wait PID system call. Okay, it is another system call. So that means that I am going to wait until the child finishes, and the child says that, okay, I don't like my core image. Okay, I don't like running whatever I am running. I am going to change myself to this command. Okay, this command is, for example, find me another command. For example, it will be where is my ls command? Let's say I'm going to be, okay, let's see, where ls. Do I have where command? No. Which ls? It is /bin/ls. So here I am going to say /bin/ls. For the parameters, maybe I am not going to give anything, then 0. Okay. So if I do that, my child process will run this program. So it is going to change its core image from this one to another program. Okay. And that program will start running. That process will start running. So I am going to change from this core image to this core image, new core image. That's what this exact with execution with environment variables. Okay, that's what the exec VE does. It replaces my core image with the new image, and it executes it, and it returns the result. This one. Yeah.
Does the address space changes after replacing the process's core image?
Did everybody hear it? Yes? No? No. Okay. Say it louder. The question is, does the address space change when we do this? And I'm going to ask you the question back to you guys. Of course, the address space changes, but when does the address space change? When I do the fork or when I do the exec VE? When does the address space change?
Yeah. Address space changes.
Address space changes when you do the fork, because the address space of P1 and P2 are different. Okay, their contents are exactly the same, but their address spaces are different. But they don't know that, right? But they don't know it because they think that they have the. I mean, the positions for their local data is the same in memory positions. The positions for the global data is the same, but in reality, they are using two different physical locations in my memory. So that's the memory virtualization, right? So the operating system, with the help of the hardware, makes this P1 and P2 think that they have their own address space, but in fact, well, they have their own address space, but they are using the same numbers to access the variable named A or B, right? But in fact, they are using different places in the memory. Did I answer your question, or?
I was asking for the exact system call. After calling the exact, does the address space change?
Okay, so I took his question wrong. Your name is you are Kamil, right?
Yeah.
Kamil. So Kamil's question is, when we do the exec VE, the address space changes. Address space change. Well, I mean, you could say yes or no. Well, it is up to the operating system to use the exact same physical location. But if the process is a new process, and address space is new too, you could say that. There is no way that I can access the local variables of this original P2. Okay. When you do the exec VE, you forget everything that you had before. So I mean, it doesn't make any difference if you are using the same address space or a different address space. Okay, it's a completely new process and it starts from the beginning. Okay, so I mean, if you're asking, can I communicate between these two? But I mean, this is done, this is gone. Okay, there is no such processes anymore. So it doesn't make any difference if they are using the same address space or different address space. Okay, good. Any other questions? Good. So some of the process management system calls are like that. So we looked at the fork, we looked at the wait, PID, and exit, and just to use them in a useful useful program, the book gives us a small shell program. Shell program is the one that we use as an interface between the end user and the operating system, and it's like this one. Remember, I am using this shell, bash shell here. Bash is my shell program. So this shell program is basically responsible basically acts as a interface between myself and the operating system. So whatever I am typing here, okay, it takes it and interprets it, and it usually translates it to an operating system call. Okay, if you write something garbage like that, it just says that doesn't make any sense. Okay, I mean, this one is not a command, I can't find it. Okay, if I am writing something meaningful like that one, okay, and it lets the operating system make this execution PS, and it works that way. So this is a very simple shell program. It runs in an infinite loop while true. Okay, it runs in an infinite loop, and this infinite loop says that, okay, I am going to give you a prompt. Prompt is this. Okay, in this case, my prompt is just my login name and my computer's name and etc. Okay. After that, I read the command from the standard input. So I read the command along with the parameters. So my command is ls-al. Okay. So this is the command. These are the parameters. And then to make a new, I am going to run that command now. To run that new command, I need to fork. I need to make a new process, and fork makes that new process. What does the fork do? Actually, it copied myself. So there are two shells running now. Okay. One of them is the parent, the other one is the child. So the two programs are running. They are exactly the same thing, but this fork returns a non-zero number for the child, for the parent, but a zero number 0 for the child. So this one says that, okay, I am the child, because fork returned a 0. If I am the child, I am going to replace my core with this new command with the parameters. ls is the command name. Parameters are the parameters of that command. So I am going to run it. It replaces, with a system call, it replaces itself with this command. But for the parent says that I am going to wait until the child ends. Okay, so it's going to be blocked here until the child ends, and then I will go to the top of the. So of course, when this exec VE ends, okay, this is not a regular function call because there is no coming back to this exec VE. Okay, so once you call this exec VE, this will never return because it changes its core image, right? So that whenever that ls command ends, that child is going to die. When the child dies, this one will be unblocked, and I will come here and I will go to the top of the loop and do the same thing again. This is what the system text-based or the console-based shell program does. It takes a text from the user, okay, it makes a fork, and it for the child process, it replaces the code image with that program, and it goes to the top of the loop and it continues that way. Yes.
So when we have this child here, we can access command and parameters from the parent, right?
No. Well, I mean, these are two different programs, okay? This command is a local variable, right? Parameters are local variable. Both of them are available for both parent and the child. It's a copy, okay? So if I am,
It's a copy, yeah.
yeah. So this is process 1 and this is process 2. Inside this process 1, I have the commands, I have the parameters. Inside process 2, I have commands and I have the parameters. Okay?
After execute, can we access it? Because you said that it changes this to another command. Changes the process, the image. It's another.
I am not understanding what you are saying.
So in the child mode, we execute this exactly. Exactly. I don't know how it's pronounced.
Exec VE, yeah.
Exactly.
Execution with environment variables.
Okay, so we have command and parameters that we copy from the parent process.
Yeah.
So now when we execute this function, we have a new process depending on the command, right?
Yeah. Yeah.
So do we now have command and parameters still? If we
What do you mean here? I mean,
address-
when this one ends up in a system call, okay? In a system call, remember this exec VE has a system call number along with the parameters. So these parameters are passed to the operating system, okay? And operating system loads the first parameter along with the other parameters. So this information is fed to the operating system, and operating system takes care of it. When that new command runs, okay, depending on the command type, the parameters are of course available to that command. Otherwise, the command cannot continue. Remember what we said about the read system call? This one. When you make a system call read and these three parameters, that exec VE another system call along with the parameters. Okay? Good. Any other questions? Yeah.
Sorry, I didn't catch what fork exactly returns.
Fork returns
Yeah,
fork
the idea-
returns either 0.
Okay.
If it returns 0, that means that you are the child process.
I don't
If
catch
it is not 0, then that means that you are the parent process, and the returned value is the new process's process ID number.
I didn't catch, but it depends. Why it turns 0 or non-zero.
It returns both of them. There are two processes, right? I executed something. I called fork. Okay? As soon as I called fork, now I have exactly the same process, and they will continue running, okay? So process 1 and process 2. After this point, it's going to be process 2, okay? Well, if for the original process that called the fork, this one is going to return a non-zero number. This one is going to return a 0 number, okay? That's how you differentiate yourself from the parent or from your child, okay? How would you know that you are the parent? How would you? Because you are exactly the same, okay? So that's the mechanism that they define. They say that for the child, this one will return a 0. And if you have such a code, okay, it just calls fork and it doesn't check the result. This is not a good code, because there is no way that you are going to know the difference between your child or with your parents. Usually, fork is called this way. You call the fork function, and you look at the returned value. If the returned value is 0, then that means that you are the child. Okay. Yes.
Can we learn child process ID?
Can we
Learn
learn
child process ID.
Yeah, well, there are system calls that will ask what is my child process ID. No, what is my process ID? What are my the memory usage case? And remember that process table. You are free to learn your process table entry that the operating system keeps for you. And basically it is, what was the PS all AFX? Yeah. So this one, see, this one say these are the environment variables. These are my process IDs, and this is what kind of terminal that I'm interacting with. I don't know what these are. I mean, you need to look up the definition, the man page of the bash. Okay, so these are all available. So if I am this process, PS process, okay, where is PS? Yeah, PS is this. So all that information is kept by the operating system in the process table, and you can ask this information from the process table by a system call. And 59 is your ID number. Okay, and this wait PID again, you can use this wait PID system call to communicate with your child processes. Okay, there are ways of, okay, see this one. So I have at the beginning this init, then init has a child bash has a child PS, and let me do this. See, I have another bash now. Can you imagine the parent? Okay, PS minus AFX. Okay, so when I hit the enter button, can you imagine what you're gonna get? You're gonna get one init, another init, then bash, then another bash, then PS, right? See, I made another bash. Bash is running now under this bash. But since this bash did not die, this bash is going to wait for it until it is over, right? So I am interacting with this bash. And if I kill, for example, if I kill this bash, this is how you kill a process, another system call. Okay, so the whole thing is gone, my window is gone, because I killed my parent's parent, which is bash, and without the bash that window doesn't make any sense anymore. So I killed the whole session. Okay, so I mean, parent-child relationship is important, because with the parent-child relationship you do some useful stuff. If you kill your parent, then all the child processes are killed automatically. Good. Oh, okay, I used too much time. I need to take some break, 15 minutes. Okay, let's be here around 11:48. Arkadaşlar camları açalım ya. Bu arada cep telefonumu götürmek zorundayım burada arkadaşlar. Lütfen. O nedenle bu kesilecek, yani internet bağlantınız. Geldiğinde açarım tekrar.
Bankacılık geçmişte bir çeşitli bilgileri var.
Adamın mesleği var mesela. Tamam mı? Bunu nasıl sayısallaştıracak? Yani bunu kodda nasıl reprezent edersin? In anlamı. Bunu bir nasıl sayısallaştırırsın? 0-1-2 olmaz. Çünkü 0-1-2 yaparsan öğrenme algoritmanın onların arasında bir ilişki olduğunu düşünüyorum. Halbuki mesleklerin arasındaki ilişki tamamen bağımsız ilişki. Tamam mı? Yani atıyorum mühendis, öğretmen, doktor koyun. Mühendise 0 ver, öğretmene 1 ver, doktora 2 ver. Bu 0'la 1 mühendiste doktor mu diyor? Mühendis öğretmen. Mühendis ve öğretmenin arasında daha yakın ilişki olduğunu düşünüyorum. Doktor 2 numara. Ayrıca öyle olmaması lazım.
Çok bilmiyoruz dedi. Soğuk. Bilmiyoruz dedi. Ne yaparız diyorlar. Yaparızdan onu kestik. Geçen sene de
Hepsi bir nöron oluyor. Fonksiyonel bir nöron. Ondan bir açıklaması var. Mesela 2 boyut yani 250 sen şöyle düşün. Verileri düşün. İki classification düşün. Biri ortada sıfırdan mesela. Birilerde böyle bir zaten onu nasıl ayrıştırsın? Ortaya bir yuvarlak çizersin. Ayrışır. Ama biz çizgi istiyoruz. 2 boyutlu şey olmaz. Yuvarlak olmaz. Ne yapıyorsun? Bu 2 boyutlu şeyi uzayı 3 boyutlu yapıyorsun. 3 boyutlu yaptığında şunu görüyorsun. Aslında şöyle bir konu 3 boyutlu düşün. Şöyle bir çukur. Ortadaki değerlerse alttakiler. Kendi değerleri bir yandakiler. Üstten baktığını düşündüğün zaman 2 boyutlu. O zaman şöyle bir çizgi şekli ayırabiliyorsun. Konuyu arttırdın. Çünkü ortadakiler altta kalıyor. Şöyle düşün.
yani konunun ucundan şöyle.
Şöyle çiziyorsun çünkü şöyle ya işte. Ortadakiler altta kalıyor çünkü altta şey altta ya. Konuyu koyuyor.
Ama hiç
yerde de kenarda olunca sen şöyle bir çizgi çevirebilirsin.
Boyutlu şeyde yıkılmış.
Aha, evet. Şimdi bu uzağa şey. Ne diyor? Yüzey mi diyor?
Düzlem.
Düzlem. Karesi kemiğe yazmış. Şöyle yapabiliriz. Bunu yapmamak için neural network yapıyoruz. Neural network'te de hani yuvarlayan şu. Şöyle birden çizgi çıktı yuvarlayan yapacağız. Neural network çok da şey değil. Hangi dersler?
Computer vision, computer interaction, database. Üçünde zaten benzer şeyler içeriyor. Computer çıkıyoruz. Ben bir tane bilmiyorum. Şu anlık değil ama seçmelere bağlı. Tadına bağlı.
Ben şeylerin içinde çok ders de yapabilirim.
Yani seçmeler arasında iki seçmeli bitirmez.
Algoritma olacak. Dönem uzaması için yaz okulu. Yazılı 2 ders olmasın.
Sen 3 ders
Bu da
seçmeli. Notu da oldu. Ya da belki de ben yaptım. Proje vardı işte.
Şey olması lazım. Buna göre evet biraz karışık. Yanlış söylüyorum. Ama burada demek ki ama yine aynı kod çalışıyor. Şu an bir şey gelemiyor. Böyle yani yeni ya da Python loop'ta falan numaralar
Prosesin Fork'un sıfır olduğu için o ifin içine girmek zorunda. Anladım böyle. Şöyle mesela önce çalıştırıyor. Şimdi return değil sonradan yapıyor. Şimdi fork'un çağırdığı zaman proses oluşturuyor. Ama bu mesaj yani return değeri burada fonksiyon önce yapıldığı için
sadece
her prosesin ayrı bir return değeri olmuş oluyor. O yüzden birisi hariç birisi de herhangi bir sayı olmuş.
çocuk için
Ben yoksa bu kağıdın yanınızda boş kağıt olan var mı? Kağıtına gerek yok ki. Bugün tarihini at, işletim sistemleri yaz. Tamam mı? Okay, so this is the program. Basically, all the bash programs, they work like this. And of course, I mean, they are not as simple as it, but the basic backbone, the skeleton of all the bash programs, text-based bash programs, the shell programs, they work like this, but there are many details, of course. For example, in my stuff, in my shell program, I can do things like what? Microphone is off and my video is off. Is it fine now? Okay. I can do things like, for example, go to the root directory and do this AL RT and recursive. Okay, so it's going to try to list all this content for me recursively, so it's going to take lots of time. So let me put this in where? Home and like that, and s.txt. If I do that, it's going to take lots of time. See, it keeps running and running and running. So I'm going to kill it. So I'm going to run it at the background if I can find. Okay, so that means that I am going to run it at the background. So see, this is 25 is the process number of my ls command. 25. It is running at the background. I don't know how long it's going to take, but the point I'm trying to make is that this simple bash program, this simple shell program, doesn't support these kind of the input output redirection, piping, and background job assignments and etc. Okay, but this one is just a simple skeleton of that such a program. I mean, shell program is much more complicated than that because I can write my own with this bash program. I can write programs like I can say things like if I don't know, I don't remember the echo is something 0, yeah, 1, and question mark, yeah, okay. So when I do this, yeah, see, question mark is the variable that is the returned value of the last running program. Okay, when I say ls s dot ls just ls and question mark, it returned a 0. It's exit 0 kind of, or return 0 kind of, so there is no problem. But when I say ls this file, no such file exists, and when I do this, so it is an error code 2 or return number 2. So I could do things like if this, so what is this? Do you know what this is? Do you know what's going on? Why am I getting this? Because that ls program is still being running, right? It is still run, and although I am redirecting all of my output to that file, I did not redirect my error output to anywhere. So it is printing the error output to the standard output, which is my console, and it's giving me all those kind of junk. Okay, so do you know how to bring that? Do you know how to bring that back? Okay, you say foreground 25. No such job. Well, it is there. FG foreground ls. Yeah, see, I brought it to the foreground, but there is no way that I can change its standard error message to somewhere else. Anyway, I'm going to kill it now. I killed it, so it is not running anymore. The point I am trying to say is that the shell programming is much more complicated than this, because all the shell programs, they have their own kind of scripting language. Okay, you can set the variables, you can get variable names, and depending on your variable names, you can write conditional statements. But in this case, my program doesn't do that. Okay, but basically this is what I do. One thing that we need to remember here is that let's talk about this. There is a system call named exit. Okay, there is a system call named exit. You make the system call, okay, and the operating system terminates your process. That's as simple as this, okay. And you provide a return number. For example, when you say exit 0, okay, terminate my process with an error code of 0. That means that I am fine now. Just terminate myself, okay. And if you say exit 2, terminate my program with an exit code of 2. Okay, that's as simple as this. In this shell program, when I say exit, okay, as expected, the whole window is gone. But let's look at here, okay. When I write, okay, exit at the prompt, okay, read command exit, okay, and I forked it, my parent says that, okay, I'm the parent, I am going to wait. The child says that, okay, I am the child, I am going to execute this system code named exit. So it changes its core from this shell to exit. An exit program will run. So what does the exit do? It just terminates itself, right? So this one terminated, and the parent says that, okay, the child terminated, I am going to the beginning. So what happened? I did not kill the child, right? I mean, sorry, I did not kill the parent. I killed the child. Child is going to be killed anyway. The point I am trying to make here is that by typing exit here and doing this fork on this exit doesn't give me the effect that I want. I want to kill the parent itself, but I keep killing the child, which is exit program. Okay? So what would be your solution? I keep writing exit, and I make another program, I make another process whose task is to execute the program named exit. And when I execute the program named exit, it terminates the child, but the parent keeps running, because parent and the child are two different processes. So what would you do? Yes?
Before fork, I would check if my command is exit. If it's exit, then I would just exit the parent code. I return the.
I am sure nobody back there heard you, but did you hear it? Did you hear that? Did you hear it? Did you hear what he said? What did he say? You didn't listen? Okay, what did you hear it? So only two people heard you. One of them didn't care what you said. Please say it louder. Okay?
Before fork, system call.
When I say it louder, say it louder.
Before fork.
Yeah, that's funny, right? That's what I am doing. Yeah.
I would check if my command is exit. If it's exit, then I would terminate my parent program.
Yeah. Exactly. Here I check if the command that I read from the keyboard is exit. Okay. You just make a strcmp. With the strcmp, if my command is same as exit, then I will say just exec ve exit, okay, or just call exit the program named exit, okay, and in that case it's going to kill your parent, the whole shell process, okay. So these kind of things you need to be careful. Other than that, this is just fine. Okay, good. So let's go back again. I am not trying to teach you how to write a shell program here. We are just trying to see what kind of program can I write with this fork and wait PID and exec v and etc. Okay, so it would be a very nice exercise to write a shell program for yourself, including the scripting, including the background processes, including the piping and redirection of the input-output, and etc. But that's kind of a classical homework for the operating system, and there are many examples of it. When I try to assign this homework, I get lots of copying from the internet, so we don't give this kind of homeworks anymore. Yes?
I have a question about shell.
About what?
Shell.
Yeah.
So you said shells has a programming language for their own purposes, like bash for.
Yeah, they had their own scripting language, not programming language, but scripting language. Yeah.
Please, is there any different use case for this bash scripting language or shell scripting languages, or is just made of for shells?
Well, I mean, I don't understand the exact point of your question, but I mean, usually those scripting languages are very similar to each other. I mean, they are not very difficult to learn, but if you like to say things like, what happens if I have those kind of scripts already available for me, and do I have to port from some other scripting language to this one? Then it is easy. You just call them, right? You could say, for example, with the bash script, okay, it is as simple as calling this BS, right? LS. I can call bash with s.txt. That means that run a bash shell on this source program s.txt. And I can do that with like C shell, okay? Run this C shell shell program, and the source code is s.txt, okay? So it is easy to use somebody else's scripts within your script file of bash. Okay, so it doesn't matter actually. The compatibility wise, it doesn't matter what script file you are using or what script program you are using. That's why we don't care about much what you are using. I mean, the design differences, the programming differences, etc. It doesn't have to be similar. It doesn't have to be the same, because the using. I mean, it is very difficult to call a C function from your Java programming language. Okay, we don't have those kind of problems here, because they are almost doing the same thing. They are almost running around the same place. As I said, I mean, I don't understand the point of your question, but the thing is that the difference are not that important. That's what I'm
So
saying.
my question actually, like Python is also a scripting language, and we are using it for very different areas.
Yeah.
Is bash usable for these two, or just shells?
So I mean, my answer is going to be the same thing too. I mean, doesn't matter. I mean, use whatever is good for you, and scripting. I mean, this shell scripting will not make your job that difficult. You can in this shell script, okay, you can call your Java program or your Python program or your C program. You will get your results back. That's what I'm saying. It is not as difficult as using a Java program and C program and a C# program at the same time. It is much easier than that, okay? So it's like a glue, okay? Very inefficient, interpretive, but it is simple enough to make all these kind of connections very easy, because you can get the results from your Java program and feed them to your C program and get the results back and feed it to your Python program using these kind of scripting tools, okay? That's why we don't call them programming languages. They are just temporary solutions. Of course, you don't do scientific computation or enterprise level software development with shell scripting. Of course, you don't do that. That's why we don't call these programming languages. But if you have many different programs written in different languages, it is easy to combine them using this shell scripting. Okay? So I don't compare Python with C shell or the bash shell. They are different things. Okay, any other questions? Okay. I think in your systems programming course, you are going to see some scripting examples. Okay. I'm going to show you some of the bash script examples. For example, add two numbers into a variable. Okay, good. Let's look at this one. Can I get that? No? Okay, how about this one? Okay. So, as you see, this is a bash script. You can do arithmetic operations doing this. There is a variable, and did you see that I did not define the variable? It's integer or not. It's an interpretive language. I add them up and I print result. One example. Let's see some while loop. Okay. When it is true, count is 1 while valid. Okay. So this is true. Do echo the printed number on the screen. If count is equal to 5, then break this loop. Otherwise, increment the count. Okay, so this one is going to print from 1 to 5, right? So immediately you understand what is going on. What else? Let's see some more complicated examples. Okay, if else. Well, it looks very weird, very ugly without the indentation. But as I said, I mean, these are not for writing thousands of lines of code, very simple code. Okay, if you end up writing thousands of lines of bash script code, that means that you are trying to do something useful that you need to do in a regular programming language. Okay, so this one takes an argument too. So usually I forget about this. I mean, I used to be proficient. I mean, it's all forgettable things. Okay, you learn it, you modify one of the example files, example scripts of bash, and later you forget about them, and whenever you need, you come back and you modify one of these two. Okay, so let's go back. So these are the system calls for the process management, fork and wait PID and execve. Of course, I did not talk about these parameters. You are going to learn them in your systems programming course. Okay, systems programming course is about this Posix interface. Okay, Posix, remember this Posix interface? It defines 100 procedure calls. You are going to learn what those procedures calls do, okay, one by one. On top of it, there are Posix libraries like the multi-threading library, and you are going to learn about them too. Okay, that's what the systems programming does. Okay, you write systems programs with the systems programming. You don't write application programs. What's a systems program? LS is a systems program, right? It gives you the files and their information in your current directory. It's not an AND program. Nobody uses this computer to run LS, right? But you use this computer to run PowerPoint or PDF Viewer or the word processing programs, okay? So that's the difference between application program and the systems program. For the systems program, you need to know your interface of the operating system very well. For the application programs, well, of course you need to know your interface of the operating system, but there are many other important things too. So let's look at the system calls regarding the file management. Of course, to use the file, you need to open it, creation of the file, opening it, and closing it. You read data from the file, write to the file. Sometimes you will say that I am not going to read it from the beginning of the file, but at some predetermined position of the file. And sometimes you get these kind of status stuff of the file. What is is it open, is it readable, writable, etc. Okay, so these are the standard Posix file management examples of file management system calls. By the way, these are not exactly system calls. Okay, that's why we say that procedure calls. This is a standard C. This is a standard C function. Let me try to the simplest C function that you can write maybe is the implementation of C function exit. I'm sure I can find it. Okay, I'm trying to find it. Exit function in C. I'm trying to find it how it works, how it makes a system call in C. No, this is just an example. Let me try to implementation of system. Okay, source code. I'm trying to show you the okay, good, this one is good, I guess. I hope it doesn't call anything else. Exit H. This is handlers. Well, this is more complicated than well, that it is doing many things. Okay. What happened? Okay. couldn't find. I was trying to find the place where it makes a system call, but I think it is running some other. It is calling some other functions before. Even the simplest exit has lots of details before it is exiting from the program. I was trying to make a point here is that these are just simple library functions. Inside the library functions, you do lots of bookkeeping. At the end of that, you make a system call, and I was going to try to show you that one, but couldn't find it now. Okay, so these are procedure calls, and at the end of each procedure call, you usually have a system call saying that, okay, I did this up to this point. Now it is a task of the operating system to get me this data from the desk. Okay, these are file management stuff, and you know all of them. Making a new directory, removing the directory, linking two things together. Okay, mounting. See this one, and you mount. In Unix we have the mounting and unmounting. In Windows we don't have that much. Let's look at these, for example, special ones, changing the maybe, yeah. Let me show you this linking first. Okay, let's assume that we have two directories. One of them is this, the other one is this. These are the names of the files in that directory. Okay, names of the files in that directory, and these are the inodes. Inode, index node. In Unix, we use the inode structure, and we are going to see the details of inodes in chapter number 5, I guess. Okay, so each file has a unique number actually. So mail has a unique number of 16. That's called inode number. Games is this, and if I define a link between these two directories, for example, if I say that this node here, okay, is the same as this memo, but only its name is different. When you open this node, you are actually opening memo. Okay, when you modify memo, okay, you are going to see the effects of that memo inside this node. So they are node and memo are linked together. Okay, and in fact the node is linked to a memo, and this is a very useful way of sharing data between the directories, and Unix supports this from the first day. Windows is kind of doing this with the names of the shortcuts, right? You say shortcut, or what do they call it when you try to make a link in Windows? They call it what? Make a shortcut. It is this, for example, when I do this, make a shortcut. So this file is not a copy of this one. It is just a shortcut for this one, or a link to this one, and I can move this anywhere I like. Okay, and they will point to the same thing. Okay, when I delete this, I did not delete the original file. I only deleted the shortcut. So Windows has something corresponding to it, but I don't think that they are using the kernel system call. But in Linux, you have a system call for this one. Mounting is another Unix specific thing. You say that, remember, for some reason my screen froze up. For example, when I say that there is only one root directory in Unix, okay, everything has to be connected to this one. But what happens if I have more than one hard disk? Okay, how am I gonna connect it to this structure? So you do the mounting. Okay, you say that this doesn't work still. Okay, let me try to open the same thing from the. Okay, So for some reason that program crashed. It doesn't respond at all. But because of the protection, okay, because of the protection, it cannot hurt anybody else. Something went wrong with that program. Maybe it is trying to execute some bad code. I don't know what it's doing. But it only hurts itself. It doesn't hurt anybody else. Rest of the operating system runs fine. I cannot get any response from this one. It shows itself fine. It is partially working, but it doesn't respond to my commands. But luckily, the operating system is robust enough to give me responses for the other stuff. Okay, so with the mounting, this is my structure. Okay, this is the root, bin directory, devices directory, libraries directory, etc. This is the mount directory. Let's say I have added another hard drive to my disk, to my system, so I can mount that hard drive at this location. So if this is the data that I like to access, okay, then by following this path, I can access it. In Windows operating system, you don't do that. In Windows operating system, you have what? You have drive letters. When you say my computer, so it says that you have a single drive. If I have another drive, okay, then it will show me as C, D, E, F, G, etc. Okay, so you need to specify the drive name, and under the drive name, you specify the files and etc. So mounting and unmounting in Unix is different than Windows. What else? The other things that could be interesting. For example, chmod changes the access privileges of a file. Time just returns the current time in seconds after January 1st, 1970, and etc. Okay. Compared to Posix, of course, Windows has its own interface. It's called Windows API, Application Programmers Interface. It's just a simple header file. It defines everything. Windows.h, okay. If you include Windows.h, you know all the Windows related function calls for your C program, and some of those functions are listed here. So this table is nice. It just tries to give you the corresponding Posix system call. For example, in Windows, you don't have fork, okay? To create a new process, there is a function named create process, and it creates a process for you and it runs it. Usually we don't, in Unix, we don't do that. We fork it and we call execve, right? Both of them. In Windows, create process does the same thing. That's why we don't have a corresponding function in Windows that does the job of the execve, execution. Okay, so because the create process does the fork and execve at the same time, so the system is different. Opening, closing files, and reading and writing, and etc. So if you have a Posix compatible program, a C program, to be able to compile that program on Windows operating system, for example, you need to get rid of all the forks, change them with the create process, and since they are not exactly the same, some of the things that works on Unix will not work for Windows. Sometimes that program will not compile at all. That's why porting from Unix to Windows, it will take some time. And most of the time, those programs will not behave exactly the same. Okay? So what else can we see? So link, none. Windows 32 does not support links. How come I did the shortcut with Windows a few minutes ago? Remember, we are talking about the operating system as the kernel of the operating system. Windows may not support, as from the kernel, the linking of two files, but the whole operating system of the Windows, it supports linking. The kernel doesn't support doesn't mean that you can do the same effect using different ways. Okay. Mounting and unmounting, again, it's not there. CH mode, changing the mode of your files, is not directly supported, okay? But there are other ways of doing the same kind of thing. For example, you don't have the kill system call in Windows, but of course we can send signals to our processes. We can kill our processes in Windows too. There are other ways of doing things. But I think I used too much of your time. I am way out of time now. Are there any questions? Where is my attendance sheet? Did everybody sign it?
Not yet.
Why is it taking so long? Because you are writing your name and you are not used to it. I hope you are not writing anybody else's name. Okay, that will be it for this for today. Tomorrow we will continue from this point on. Okay.